So why all the talk about pH? Well, pH is important in so many things. It's important in digesting food. It's important um, in development of biological systems. There are certain pHs that are crucial in different parts of a plant or animal body. So we already learned that tomatoes and lemons are acidic in the previous slide. Our stomach acids are very acidic. So in our stomach, it's very acidic, but in our blood, it must be neutral. Um, in industrial processes and cleaning agents and all kinds of things, pH is involved in almost everything you can imagine. Um, but in soils, pH is going to have a direct and significant impact on the general availability and concentrations of the nutrient elements, the 17 essential nutrient elements, as well as a couple others that are important to plant growth. Not only the available nutrients goes up and down depending on the pH, also toxins that might be in the soil. So for example, something like aluminum at a neutral pH is non-toxic to plants, even though aluminum is all over the world and all the soils of the world. It's extremely common, but it's usually unimportant, irrelevant, because it's not soluble at neutral or alkaline pHs. But in acid soils, aluminum can become very toxic. So not only is it important to the plants and the available nutrients, but all of the other biological entities that are living in that soil, the fungi, the bacteria, the insects, they all depend on the soil pH. The rate of decomposition of material that is being recycled in the soil, pH is crucial. So I've talked about the availability of nutrients already and the concentration of toxins. So I explained them before drawing up or bringing those lines up. So this is a very important summary of pH in soils. So first I want to talk about this slide briefly so you understand what is going on here. From left to right, we have the pH scale. So from 4.5 to 8.0. Why only those numbers? Well, these are soils, so typical productive soils. Not all soils of the crust of the earth are going to be in this range, but certainly productive soils from an agricultural or most environmental situations are going to be somewhere in this range, 4.5 to 8. You start getting too much past 8 in the alkaline side, and you have some biological issues where it's hard for things to grow. And the same thing is true in the acid side. So this is realistic soils that you might be producing something. Now, top to bottom, you have all of these colored bands with the names of the nutrients, and the band changes width. So if we look at nitrate, the most important form of nitrogen for plants to absorb is nitrate. And you'll notice that the band of blue for nitrate changes its width. It's very, very wide between 6 and maybe 7.3 or something. And then after that, it starts to drop down, especially after 7.5 to 8. You can see the width gets narrower and narrower as we approach 8. And the same thing is true below pH 6 and especially below pH 5.5. You can see it gets very narrow in the acid, which means that the amount of availability of nitrate for plants in soil is highest in the neutral to slightly acid soils. As you move to an alkaline soil or basic soil, you start to have a less available nitrate in the soil. When you get into the highly acid soils, the same thing is true. Potassium has a similar pattern, but not quite as strong. Calcium, a very strong pattern. Calcium has very low availability in acid soils all the way up to neutral, and it is only when you start getting into slightly acid soils around 7.3, 7.5 that plants can easily get calcium out of the soil, becomes available, and it becomes extremely available in alkaline soils. But if you try to favor the calcium, look what happens to the iron, the green dotted one. I'll skip over the phosphorus. Look at what happens to iron. Iron is almost a mirror image of calcium, where it becomes extremely hard for plants to get iron in an alkaline soil and extremely easy for plants to get iron in an acid soil. Now, plants don't need very much iron. It's a micronutrient. So as long as you're in a range, slightly acidic range, iron's pretty easy for plants to get enough. But you get much above pH 7, you start to have some problems with getting iron. And so you have to maybe think about that. Now, all of these except for one on this chart are nutrients. The one exception is this pink wedge over here, aluminum. And aluminum, as I mentioned earlier, is something that's not a problem for plants at a neutral pH. Even though aluminum might be there, it's not soluble at neutral pH. It's not soluble at an alkaline pH. It only starts to become soluble when you start to get into a fairly acid soil around pH 5.4. And because the soil pH and the root zone pH can vary a little bit, you don't want to get too close to that line. Even though the soil might be pH 5.6, you might have some pH 5.4, 5.3 right around the root. And so they might be absorbing some aluminum even if the pH isn't quite down that far. So you never want to get too close to this if you have very sensitive plants for aluminum. You don't have to memorize this chart, but I would suggest that you memorize these two statements. In highly acidic soils, calcium, phosphorus, and magnesium become chemically unavailable to plants. Okay? Highly acidic soils, that's the left side. Calcium, unavailable. Phosphorus, the brown one just below it, and magnesium, which is this light blue here. Magnesium also starts to go down. So in highly acidic soils, you get problems with calcium, phosphorus, and magnesium. While manganese, here's manganese, this kind of a bluish purple with black dots, the manganese can become toxic as well as aluminum. Manganese is a micronutrient. Now, I've never heard of plants taking up too much iron and becoming toxic, although I assume it might be possible. Manganese, on the other hand, can become toxic, very much so. On the other hand, in highly alkaline soils, micronutrients like iron, this one right here, zinc, this one right here, and copper become chemically unavailable to plants. So again, the reason that pH is so important, well, one reason is the availability of nutrients and toxins. So there's a reading that you will get that shows these pictures, but this is actually not directly a set of photos taken by adjusting the pH. These are photos taken by depriving some tomato plants of certain nutrients. So a subset of the 17 essential nutrients are shown here in an experiment where these plants have been deprived of these nutrients. And you could simulate the same kind of a thing by adjusting the pH, but it wouldn't be as dramatic as you see here for the photograph. So this is done in a laboratory environment to dramatize the effects of the unavailability of these nutrients and how it interferes with the plant's development. Now, all plants have a particular preferred range where they normally like the pH to be for their most healthy, their most rapid growth. This generally goes back to the center of origin, or where the plants originally evolved on Earth. And we can adjust that to a certain extent with our breeding. We can breed to give plants a little more tolerance to higher or lower pH, but for the most part, plants tend to fall into a range that is important for the plants to be able to grow as happy, healthy, and productive as possible. And some of the acid lovers, you'll notice that a lot of the ones in here have the word berry: blackberry, blueberry, strawberry. They all are. Tomato is a type of berry. All of them are acid lovers, but there's others like pumpkins and watermelons and squash, corn. So a lot of different things that are acid lovers. Now, how much acid? This doesn't exactly say, but some of the berries might like the extreme acids in the pH 5s. And some of the other entries on this list might be happier to pH 6. The neutral one, slightly acid to neutral. There are many things here that we might recognize, things that we grow here like spinach. A lot of mustard grows in this area, cucumbers, Brussels sprouts. We grow lots of Brussels sprouts in the coast area near Watsonville, etc. Garlic. This is the garlic capital around here. So again, lots of things that we would recognize in this area as slightly acid to neutral lovers. And then the neutral to alkaline, a lot of things that we also grow here, the crucifers or cole crops like broccoli, cabbage, cauliflower, and broccoli with, or no, broccoli, cabbage, cauliflower. What was the other one? Doesn't matter. Lettuce. Lettuce is the #1 crop in our local area. And onions, we grow lots of onions in the area here. And you might say, well, wait a minute, aren't they growing strawberries and lettuce in the same field? They'll follow one with another. How the heck do they do that? Well, by managing your soil amendments and managing how you choose to fertilize, you can manipulate a lot. And just because the plants are adapted to a particular pH, you still have a lot of ability to manipulate the plant, keep it happy by making sure it gets the nutrients it needs. But it's not just the plants. It might also be the diseases. So for example, with broccoli, they get something called clubroot. And the clubroot is a horrible bacterial disease that causes some serious problems. And it loves neutral soils. So by growing the broccoli in a slightly alkaline soil, you can make the broccoli really, really happy and the clubroot not so happy. And you can reduce your incidence of clubroot a whole lot just by manipulating the pH. So how do we measure that? Well, there's lots of ways, from the cheapest analog meters, which actually do a not too bad job as long as you calibrate them, to handheld pocket meters, test kits, chemical test kits, which give you the pH based on color. Now a kit like this looks like it's doing a lot more than pH. And tabletop meters, which are more sophisticated. This is kind of a simplistic device. They can be up to thousands of dollars in, recording things on a computer. pH is trickier than it seems. I would highly recommend that you always question the pH meter that you have. Look at the manual, look at the instructions for how to properly calibrate it and use it. Call the manufacturer and just say, hey, manufacturer, where's your technical sales representative people? Who do I call? and then ask them, we've got these meters and we're using them for blah, blah, blah in our ag program. Is that an appropriate use of this meter? I would say more often than not, the one tool I've seen misused more than any other is a pH meter, where people are using a pH meter that's not appropriate for the job. Some pH meters just don't do a good job with soils. They're not durable enough. Some pH meters just absolutely cannot measure well water. Well water is notoriously difficult to measure because there's just not enough salts in it. You don't want salty well water. It's supposed to be fresh water. And fresh water is really hard to measure the pH. So what do? You use a meter that's designed to handle the low salt conditions of well water. Otherwise, any pH meter is going to give you a number. Just because it gives you a damn number doesn't mean the number is accurate. Doesn't mean it's right. Know what you're doing, and I don't care how many times your boss tells you this is the tool, this is what you do. Take some time to look it up and make sure, is this really a good meter for this application? Is this the meter we should be using? And then you got another problem if you talk to the sales rep, and they go, oh, no, I would never use that meter for that. That meter really isn't designed for that kind of application. Now, how are you going to tell your boss that what they've been doing is all wrong? That's your problem, not mine. But again, you've got to use the right meter, the right probe, because a lot of meters have interchangeable probes, not most of the pocket ones. But the desktop ones, you plug in the appropriate probe. The unit doesn't matter. The probe plugs in as a separate accessory, and you have to make sure that the probe you're using is appropriate for what you're measuring. Okay, enough on that. The next topic is buffers, because pH is just one piece of the puzzle. pH is like a snapshot. What is my hydrogen ion activity at this very moment? That's the pH. But there are other things, chemicals in the soil or whatever solution in your stomach, in your blood. There are chemicals in biological and natural systems in the inorganic environment, in manufacturing processes that can release or absorb hydrogen ions and resist changes to the pH. We call those buffers. So as I just mentioned, soil pH is just one number and does not give you the soil pH whole story. There's also buffers to be worried about. Buffers are compounds in the soil that act as hydrogen ion reservoirs, meaning they can combine with hydrogen ions, take them out of solution, effectively removing them from the soil moisture, and they may release more hydrogen ions. So effectively, a buffer is a chemical that resists changes to the soil pH. All right. And before I get into buffers any deeper, I'm going to take another break.